Okay, this is a video on reading oscilloscopes. Now, I've got a picture here of an oscilloscope waveform. And one of the things I want to talk about is newer scopes and older scopes. And if the picture goes away, then I will pull the picture back in. Newer scopes have the vertical and horizontal divisions usually on the screen. So like in this picture, this is a newer scope, even though it's a number of years old, and it's telling me that I've got 1 volt per. And so my voltage typically on an oscilloscope is up and down. So each of these little squares represents 1 volt. As I change my range knob on the oscilloscope, you'll see this number change. Okay? The same is true for time. So each square, and time is always going to be your horizontal or your x-axis. So each of these squares is worth 500, and that's the lowercase u. That's the microseconds. So each of these squares represents 500 microseconds. So newer scopes, the display is usually on the window. And so if you know to look for that and you see what the display setting is, then you can actually tell what the waveform value is in terms of voltage levels and frequency. Older scopes, you won't see the display of the volts per and the time per division. That's usually on the knob that you turn when you make the adjustments on the older scopes. So whether it's a newer scope or an older scope, there is an adjustment for volts per division and time per division. Now on this scope, there's a button down here where you press and you set your probe. And oscopes have a probe multiplier. So you can have a 1-to-1 multiplier. In other words, the signal in is the signal displayed, or you can have a 10-to-1 or 100-to-1 or 5-to-1 or 20-to-1. Older scopes usually only have 1-to-1 and 10-to-1. Newer scopes have a wider variety of ranges. So your multiplier can be set based on what the scope probe's got. And a lot of scope probes have a little switch on it with a multiplier switch. So it'll have like a 1x on it and maybe a 10x. What is set on the scope probe, the scope probe wire has to match what is set in the probe on the oscilloscope. So the multipliers must match. If the multipliers don't match, then this volts per division could be off by a factor of 10 or 100 or whatever. The time per division won't change. It's just volts only. So your up and down could be off by a multiplier if your multiplier is mismatched. So that's one of the things you got to look at. Look at your scope probe and see if the little switch is on 1-to-1 or 10-to-1. The other option on that probe is ground, and that is for zeroing the signal. So you won't typically use that setting for measurement. Like never. You'll never use that setting for measurement. So your multiplier should be 1-to-1, and I suggest you start out 1-to-1. And you got to make sure your probe is set for 1-to-1 or your vertical readings could be off. Okay? This scope also talks about coupling, and the coupling is DC. And DC coupling will show an AC waveform, which is what I've got here, and it will show any DC levels that are combined with that AC waveform. So DC coupling will show you DC, and it will show you AC. AC coupling will only show you AC, and what it does when you go to AC coupling is it centers the waveform around 0, which is what this one's actually doing, but you could have some offset, sometimes you won't. So you can read AC on DC coupling. So normally that's where you start on DC coupling. If your DC level is so small and your AC level is big enough, then you would then go to AC coupling to make a reading. In this case, we're going to read an AC waveform on DC coupling. Some oscilloscopes have calibration knobs, and the calibration knobs usually click if you turn them clockwise, and that is the calibrated position. There is a setting on the oscilloscope once you get really into it where you would sometimes turn those knobs where they are not calibrated off of the cal position. But when they're calibrated, then your horizontal time is right. Now, it could be off because the calibration of the instrument drifted. But if it says 500 microseconds, then each square is worth 500 microseconds. If you're on an older scope and you've got 500 microseconds, but your calibration knob is tweaked away from full clockwise, then it'll say it's 500 microseconds, but each of these squares will no longer represent that. So that's some of the things you got to do to get everything set up right. What you want to do is you want to look for the volts per division, check your multiplier, make sure you see time per division. If you see it on the screen, great. If you don't see it on the screen, then look for it next to the knobs and how the knobs are set if you've got an older oscilloscope. So that's what you got to look for. Everything set correctly. All your cal knobs should be turned clockwise. Coupling on DC. Multiplier, all that. That's what you got to get right first. Once you do that, and I'm going to scroll this down, which will make my drawing go away, or my picture, but I'll bring it back. There we go. Once we get that done and we know everything is set up right, now we can make a measurement. So each of these squares is worth 1 volt. So in the electrical field, we have 3 types of voltages that we like to talk about. And they're listed as VPP, VP, and V. Now, and I've seen textbooks where people will ask for a peak-to-peak voltage, or VP to P. They'll ask for a VP voltage. They'll tell you it's a V. So the subscripts here, even though I didn't make them subscripts, the P's here should be subscripts, and the lack of P is important also because it tells you what voltage type that they're wanting. Okay, peak to peak is simply from top to bottom, and that's what the P to P stands for. It's peak to peak, so it's peak to peak. All right, go back to the picture, peak to peak. All right, so here's a peak. Here's a peak. How many squares are there between the peaks? So I count 1, 2, 3, 4. And each square is worth how many volts? I forgot. Oh, wait, 1 volt. So 4 times 1 is 4. So this signal is 4 volts peak to peak. 4 volts peak to peak. I'll capitalize the V to make it a little easier because that's easier than subscripting the other. Okay. Now the other range is peak voltage, and peak voltage is from the 0. In this case, the 0 is this center line right here on the oscilloscope. It's got the extra hash marks on it. So if I go from the center line to the top peak, then what you see is I've got 2 squares. So looking at the same waveform, this is now voltage peak, and that's assuming it's referenced from 0, and in this case it's 2 VP. Okay? So if somebody tells you to set a 2 volts peak to peak waveform or a 2 volts peak waveform, they're asking you to do the same thing. So it's very important to look at what they ask for specifically. Now, The V level is the RMS level. And a lot of scopes will have a display that comes into what the V level is, and I'm going to talk about that down here in the bottom when we get to sine wave relationships. Your oscilloscope will not necessarily show you the V or the RMS value, so it's an RMS value. The VRMS value is what a multimeter reads, and I might go back and put that in later, or I'll capture it down here. I'm not sure yet. We'll see how this goes. So those are the voltages. Okay? I'm going to tell you down here that for a sine wave, in order to be complete, the RMS is about 71% of the peak voltage. So if I take 2 and I multiply it by 0.71, I get about 14.1. Excuse me. 2 times 0.71, I get about 1.41. 1.42 if I do 72. So let's just do that. There we go. And my unit would be volts. So same waveform. Same waveform. I can tell you I want a 1.242 volt signal. I can tell you I want 2 volts peak signal. I can tell you I want 2 volts peak to peak, and I'm asking for the same signal that you see right here on this waveform. Now the period. The period is the horizontal squares. And when you're measuring the period, you either go, and this is a judgment call on your part, what's convenient. So you want to go from where the waveform peaks to the next peak. You can go from where it crosses 0 going positive to the next point that it crosses 0 going positive. You can go from a negative peak to a negative peak. It doesn't really matter, but what you're looking for is one complete cycle. So if I start at the bottom and I go through one complete cycle, I max and I'm back where I started. If I start at the top and I go through a cycle, I go through a minimum and go back. If I start at 0, then I get a positive peak, a negative peak, and I'm back. It's all the same distance. All the same distance. And that's what's important. And so the period of this waveform, then we would count squares. So 1 square. So if I do it from the center line where it crosses 0, so that's 1 square, that's 2 square, and that's 1, 2, about 3/10. So it's 2.3 squares, and my time per division is 500. Okay? So what is that? That's 1,000, right? 2 squares would be 1,000. 1,100, 1,200, 1,300 microseconds. So my period is now 1,300 microseconds. And I got that just from counting. If I go from this peak to this peak, I get about 2 full squares plus 3. If I go from valley to valley, I get about 2 full squares plus 3. It's really a judgment call. Now, the oscilloscope is showing you the period. It's not showing you the frequency. You have to do a little math. And to do a little math, what I've got to do is invert this. So I'm going to take my 1,300 microseconds and I'm going to convert it to seconds, which means I got to move my decimal 6 places. So it's 0.013 if I did it right, right? 1, 2, 3, 4, 5, 6. No, I need one more. One more. So 1, 2, 3, 4, 5, 6. So 2 zeros, 1 3, and my unit is seconds. And that's why we started out in the class doing engineering units, because this is an engineering unit. I want to go back to base units. Frequency is 1 over period. So F equals 1 divided by T. And the same relationship is true. Period is equal to 1 over frequency. So if you're given one, you can get the other. So in this case, the oscilloscope is giving me the period of 0.0013 seconds, and I want to know what frequency that is. So I go into my handy dandy math program, and I'll do 1 divided by 0.0013. Now this is why I converted it to seconds, because when I do this in seconds, then my answer comes out in what we call hertz. So about 769 hertz. And now I got to find the right. There we go. Okay, so my frequency is about 769 hertz. Okay, so if I want a frequency of a certain level, I take that frequency in hertz and I 1 over it, and then it tells me the period of the waveform I need to set. So if I took 769 and I 1 overed it, I'd get the 0.0013 or 1300 microseconds. So then I could adjust my waveform so that it covered 1, 2, and 12.3 squares. And I would have it. I would have that frequency. Okay? So all the information is there. That's the whole point of the video. If I know the volts per division, I know the seconds per division, and I see a waveform, I can come up with its voltage and I can come up with its frequency all day long. Any oscilloscope. Okay, there are more options to oscilloscopes, more different settings that can be on, etc., etc. But for measuring just your basic waveform, this is the fundamentals. Okay. Now, sine wave. Well, if I look up here to the top, what's my sine wave relationships? My volts peak to peak and my volts peak means that my volts peak to peak is actually 2 times my volts peak, right? So it was a sine wave in the picture. If I take my 2 volts peak sine wave and I multiply it by 2, I get 4, and now it's 4 volts peak to peak. And that's what happens with the sine wave. Now what I told you earlier was volts peak to volts, which I went ahead and calculated. It's actually the square root of 2 over 2. Or the square root of 2 times the V to get there. Okay? Square root of 2 over 2 is the ratio. So square root of 2, oh no, he's doing square root, divided by 2, and that's equal to about 0.07071. Okay? Now what I do is I say, okay, just remember 70% or 71%. Whoops. Equals 71%. Okay? If you don't like 71, make it 70. Make it 7/10. It's going to be close enough. You're just looking to get in the ballpark. Okay? So my V is going to be about 0.7 times my VP. And that's how I got this number up here. I actually used 0.71. So 0.071 VP is my V. And so if I've got a V and I want to get my VP, then I divide by the 0.71. So I can go back and forth between these two just with a little bit of math. Okay? This one is the important one to remember because it's going to change when we change waveforms. So let's make that bold. All right. And instead of 2, we'll say equals. And we will move that down a little bit so we can sort of see the relationships. Okay, now move down to what we call a sawtooth or a triangle waveform. Well, a sawtooth waveform is not going to be as nice or not going to have as much voltage as this sine wave. It's going to be nice, pointy, and square. And so we actually lose a little bit when we go from VP to V. So the relationship holds, just like up here. My VPP is equal to 2 times my VP. But my VP is compared to my V it's now 0.5 or 1/2 equals. Now, if you remember back years ago when you did the area of a triangle, it was 1/2 base times height. So that 1/2 was the area. And so it's kind of neat that that formula helps me remember anyway that it's a 1/2 multiplier. But only for a triangle or a sawtooth. If I go to a sine wave, it's a 0.71 multiplier. Okay? So now square wave. VP to VPP is, again, a 2 multiplier. So in my voltage peak to peak to my voltage peak is the same regardless of my waveform. And when I get to a square wave, it's actually a 1-to-1. So my multiplier is 1. If it helps you, I can put a 1 here, 1 times. But most people don't put down 1 times. Your VP is equal to your V for a square wave. Okay? So when you're setting a waveform, typically you'll be asked to do a sine wave, a triangle wave, or a square wave. And so the first question that comes up with students is, hey, can I set this waveform with my multimeter? And yes, you can. If you can convert to the voltage value of the waveform wanted, that is what your multimeter will read. So if somebody gives you peak to peak and you can convert it to V, sine, square, or triangle, then you know the number that your multimeter should read, the digital number that your multimeter should read. Frequency is frequency. So it doesn't matter whether it's sine wave, square wave, or triangle wave, your multimeter is going to report the frequency. So if somebody tells you they want 1 volt peak, 1,000 hertz or 1K hertz sine wave, then 1 volt peak would be 7/10. So your meter would need to read 7/10, and your frequency would need to be 1,000. And so then you would adjust your function generator to until your meter got the 1,000 right and the 0.7, because I said sine wave. And then you'd have 1 volt peak, 1,000 hertz waveform. And a lot of students like doing that once they figure out how to do it. And you need some of both. There are other buttons on your waveform generator. Now I'm talking about waveform generators. And this is where you would adjust what you see here. So with the waveform generator, I can make this bigger or smaller, up and down, and I can make it scrunch up or stretch out if I change the frequency. So the oscilloscope will always just measure what it sees. The function generator will actually change the amplitude and the frequency. Okay? So function generators, okay, it's got a lot of buttons on it. One of them is duty cycle. You want your duty cycle to be off or set at 50%. That's probably the one that gets most people in trouble. You want a 50% duty cycle. If my would cooperate, 50% or off. That's going to give you a nice sine wave, mathematical sine wave. Wave type is selectable on a function generator. Generally, there's a button to push, whether you want a sine wave, a square wave, or a triangle. And then you're looking for frequency. Most of them have a frequency knob, and most of the function generators I deal with are on the left end. And sometimes there's a display that displays the frequency that it's actually outputting. Sometimes there is a button where you can select the frequency range. So sometimes you got to get the frequency range button right for a certain frequency. And then the amplitude is usually at the other end. So a value for amplitude, so you can make the signal go up and down. So when you put a function generator on an oscilloscope and you mess with the frequency button, you change the frequency button, you'll see this stretch out or scrunch up. And if you change the value, you'll see it go up and down. So that is reading an oscilloscope and a little bit about setting it. This is by no means everything. You've got to get a function generator, you've got to get an oscilloscope, and then you've got to get a list of set this waveform, set this waveform, set this waveform. So you get the feel for how you're doing it. These relationships that I outlined, they won't change. So you can set them with a multimeter if you want to. If you want to do a little bit of math up front, you can set them. If it's a square wave, it's easy. Your peak is your what we call the RMS voltage, or what the meter reads. So square wave's the easiest. And then triangle's probably second. Sine wave you'll do most of the time, so 70 or 71%. Or square root 2/2 if you want to be more precise. But again, you're just coming up with a ballpark figure. And I hope this helps in terms of reading it. And I thank you for watching.